The second one, the difference between finding f of 0 is that you're finding the x of 0.
Oh, yeah. Yeah. Like I grabbed it. Yeah, right. Yeah, those are tricky.
All right, folks, good morning. Let's come together as a group and discuss these. Let's start with the first one. When you see an expression like f of 3, what are you doing? And what are the 4 steps? What are the 4 steps? I wonder what on earth I was thinking when I said 4 steps. Well, first of all, when you see f of 3, what does that mean? Wait, now, hold on. You're in the front row. What's your name again? Urban, that's right. Okay, Urban. So what are we doing? Yeah, you're plugging in 3, right? So who knows what the function is? It doesn't say what the function is. Let's just pretend the function is something like x squared minus 9. And it's saying to just plug in 3, whatever that might be. And when I said one of the 4 steps, and maybe seeing that, that's why everyone was so quiet, like, what on earth are the 4 steps? What are we talking about? I'm not sure why I wrote that, but what would be the first step? You just write it empty. That way you know where to plug your number. What would be the next step? You just plug it in, whatever that might be. We're just going to make up 4 steps. So then you plug in the number 3. All right. Then you have to, what's the next step would be, you do arithmetic. So I'm going to go ahead and do the arithmetic of 9 minus 9, which is 0. And then what would be the next thing to do? To actually interpret this.
Write it in notation.
Yeah, you write it in what notation?
The function notation.
Interval. I hear a lot of different possibilities. So in function notation, it's already written as a function. What we're saying is f of 3 equals 0. Now, interval notation is when you have a variety of answers that you want to say are part of your solution set. This is not a variety of answers. This is one answer. You plug in 3, it equals 0. And yes, it's a coordinate. So now I know that f of 3 equals 0 is the same thing as a coordinate. And then what can I do now? Now that I know that I input 3, I output 0, that's a coordinate. And the last thing I can do is plug it in where? Yeah, actually make a graph of it. So I go like this. So I'd like us to all just kind of look at that for a second and realize that this expression right here is packed full of meaning. Like, look at everything that just came out of it. Like, when we just say something very simple like f of 3, which looks so benign and so harmless. Oh, f of 3. And yet, what does it mean? It means we have some function. It means you can write it empty, plug in your number, do the arithmetic, and then you have some sort of input-output, which represents a coordinate, which represents some point on the graph. Right? So this is really dense with meaning, f of 3. There's a lot of meaning that you can unpack out of it. So, you know, someday you're out at a restaurant, you're on a first date, and they're like, hey, what's f of 3 mean? And you're like, you got 5 minutes? Right? Because it would take a while to really get into the full depth of what's going on when you just say something like f of 3. Okay, I believe that's everything I was thinking when I wrote that question. All right, so now what's the difference between finding f of 0 and f of x equals 0? What's the difference between those two? Who'd like to volunteer to cover f of 0? What is f of 0, Chelsea?
F of 0 is going to be the x coordinate on the graph, or you're solving for x coordinate.
Well, if you have f of 0, then your input value is x equals 0. So you're not solving for an x coordinate. You're saying already that the x coordinate is 0. So that's true. I would know now that my x value is 0. And what else does f of 0 represent?
The y.
Yeah, it's going to be the y-intercept. So when I do plug in 0, I'll stick with my example here of x squared minus 9. If I plug in the zeros, that'd be 0 squared minus 9, which is 0 minus 9, which is negative 9. then that gives me, well, look at that, a y-intercept down here. So there's my y-intercept. So f of 0, no matter what function you're ever talking about, is always going to be the y-intercept, because it implies that if you input 0, you output some number, and so long as x is 0, you're always talking about a coordinate that's on the y-axis. So f of 0 absolutely always represents the y-intercept, and I typically just make a little dash on the y-axis, and I call it f of 0, and I say, hey, that's the y-intercept. So that's the first one. How about the second one? What's the difference between finding f of 0 and f of x equals 0? Well, first of all, what is f of x equals 0? This one would be the actual x-intercept. So if I go ahead and down right here and I say, well, when f of x equals 0, what does that even mean? Again, if I plug in some number x, that's my input, and I output some number 0, that's my output, then what I'm looking at is some coordinate of the form x comma 0. And if the form of the coordinate is x comma 0, that means I go right or left x units, and I go up or down nothing. And if I go up or down nothing, that means I'm sitting on the x-axis. So this right here would be the point where f of x equals 0. We're talking about the x-intercept. Okay, and then what's the difference between finding them? What process are you doing for f of 0? Yeah, you're just doing regular old arithmetic. You're just plugging in a number, and then you're calculating it, say on your calculator. What about this process when you said f of x equals 0? What's it say like that? Math. That's when you're doing real math. And by real math, we mean algebra. Yeah, we're doing actual algebra here. And this algebra really is the substance of this course. Well, of any course, Math 150 or 120 or even beyond. You're really just talking about how do you set a function equal to 0 and then how do you solve it? Because so many different contexts. You know, if you just had a function that was a linear function and you set that equal to 0, that's pretty easy. But if you set a quadratic equal to 0, well, that's a little more demanding. And if you set a square root function equal to 0, that's a slightly different technique. And if you set some sort of rational expression equal to 0, well, then once again, that's a slightly different technique. So depending on which function you're even looking at, taking a function and setting the equal to 0, well, that's the stuff of life right here. This is ultimately what you spend so much time in a math class learning, is given any function that you could imagine, how do you set that thing equal to 0 and solve for x? So this is a very big picture idea right here, is that much of what you learn in a math class is solving for those x-intercepts. Which might sound weird. If someone walked up to you on the street and was like, hey, do you know that most of what you do in algebra class your whole life long is learning to find x-intercepts? Probably hear that and be like, really? That's what I've been doing this whole time? It's finding x-intercepts? That seems a little weird, but it's true. Okay, there we go. The domain of a function is all real numbers except those numbers that cause you to, what's one thing? Yeah, you can't divide by 0. So the domain of a function is all the real numbers except those numbers that would cause you to either divide by 0 or square root of negative. Those are the two things you're not allowed to do, and therefore those are the input numbers that we exclude from the domain. And finally, how often should you graph a function before solving it? Yeah, I would say every time, right? That's kind of a trick question. How often should you look at the graph? Only always, because the graph is the visual representation of what this function even represents. And furthermore, instead of solving a function, right? Like I just said, hey, here's a list of a whole bunch of equations that I want you to set equal to 0 and solve for x using algebra. Well, you don't even have to, if you really want the answer for when these things are equal to 0, you don't even have to do any algebra. You can just graph it on Desmos or your TI, and wherever that graph crosses the x-axis, you just found the answer for x. And see, isn't that glorious? Isn't that beautiful? That any equation you ever want to solve in your whole life, any equation you ever want to solve in your whole life, you can just graph it, and wherever those x-intercepts are, that is the solution to the equation. And that's a little mind-blowing, a little bit, to think that you can just sidestep all algebra, graph it, and just look at those x-intercepts, because the x-intercepts are the solutions for the equation. All right, well, that's it for the questions, everybody. Welcome back to class. Hey, this is Monday, and we've got our schedule coming up here. Don't we have another day off coming up soon? Is it President's Day, February 18th? Okay, good gumdrops. All right, so let's talk about our calendar. Today is what? Today's the 28th. There we are. Okay, so here we are. Today's the 28th. It has a schedule for 1.6, but I think what we have to do is finish 1.5 first. So, and I think we'll be able to do a big catch-up today to do all three of them, 1.5, 1.6, 1.7. And then what was due today? I think all that's due today is 1.4, right? Yeah, 1.3 and 1.4, because we didn't finish 1.5. And I updated those due dates, and a few of you emailed me about those due dates, and I made sure that it was all correct in the system, because I think the due date for 1.5 was weird. I went in and looked at it. The due date for 1.5 was like December of 1963. I don't know how that happened. It was very weird. But that's fixed now, so thank you for your emails. Yeah, and generally speaking, just keep emailing me, folks. I would say that about maybe half of you are emailing me with some regularity, but the other half of you, I don't know what happens to you the rest of the week. So, you know, please feel free to email me. Okay, any questions about what we're doing and where we're going? All right, well, I've got a math joke to start our day, and this is a classic one. Why is the math book always so unhappy? Why is the math book always so unhappy? He has so many problems. All right, so this is where we left off, right, folks? We left off in these word problems. Everybody was really excited. We started doing word problems. And I told you one of my other favorite math jokes, which is that everybody's favorite F word in math is fractions, and everybody's second favorite F word is word problems. So, did we do number 3?
Yeah.
I think we did. And then number 4, well, number 4 we looked at it, right? But we didn't actually do it? Oh, we did number 4 as well. Okay, well, that's wonderful. I just don't know that, oh yeah, we didn't finish interpreting T of 6 and T of 12. So let's just compare answers, right? Because theoretically you all went home and did that on your own. So T of 6. So first of all, this was nice. We had a whole warm-up question. What does that represent? Right? So you're on a first date. Someone's like, hey, what does T of 6 represent? You're like, we got 5 minutes. Let me tell you everything it represents. So what would we do? We would write down our function empty, that function. So that's negative 1/2 something squared plus 8 something plus t. And then we plug in the number 6, and then we go about doing a whole bunch of arithmetic. So 6 squared is 36, half that is 18, negative 18, plus 18 plus 6 is 48, plus 3. And so that would be, oh, I don't know, 33? All right. So what on earth does that mean? That means that 6 is our input, 33 is our output. We also know from the context of the word problem that what's little t? What is little t?
Hours.
Yeah, t hours after 6 a.m. So little t, this 6 right here, I'm going to write a coordinate, 6, comma 33. This is hours after 6 a.m. And look how nice this is to actually just write it down. Right? Like here's my coordinate, input, output, 633. I'm going to label it with the information the word problem gave me. T, little t, represents hours after 6 a.m. So what is 6 hours after 6 a.m.? Yeah, 12 p.m. So that's 12 noon. All right, and then what does the 33 represent? That's big T, and that's degrees in Fahrenheit. So now I can say 33 is degrees Fahrenheit. Which, by the way, that's not very hot. What does it feel like if it's 33 degrees Fahrenheit? Washington? Yeah, I mean, that's just 1 degree better than freezing. Right? 32 degrees is freezing ice, so it's pretty cold. Okay, well, that's the whole problem. So when they say find the T of 6, I found it, it's 33. But when we say interpret T of 6, it means at noon, the temperature is 33 degrees Fahrenheit. Right, and that's what you'd say. Okay, so I won't do T of 12 because that would work the exact same way. So let's go ahead and take a look at this last word problem. I will go ahead and say this is an important word problem because it's on your practice test. And if it's on your practice test, that might mean that it's on your real test. So let's make sure everyone feels really comfortable with this. So we have a function now. I'm going to put 5 right here. We've got c of x equals x squared minus 10x plus 1/7. So I would recommend that you always want to label your units so you know what you're talking about. So let's keep reading. The function c of x models the cost in hundreds of dollars to produce x thousand pens. So first of all, what does the input x represent? Thousands of pens. And so I'm going to go and write that. I'm going to draw a little arrow there, and I'm going to say that's thousands of pens. Okay, and then what did the function itself represent? What did that c represent?
Cost.
Yeah, that's cost in hundreds. Cost in hundreds. Now, I want you to notice that the way I have my arrows drawn here, X is the input, that's definitely thousands of pens. So if I input the number 5, what are we really saying? 5,000 pens, right? Now, the C, which obviously represents cost, it might feel a little confusing to point the arrow here at the C, although that makes it obvious that C is cost, C represents cost. But really, the cost is what this whole expression is equaling. That whole thing, when you actually calculate it, that's the cost, right? So while it's obvious that X is representing the thousands of pens, the C represents the cost, but that's what this whole thing is going to equal. So when you're all done calculating that with arithmetic, that's where the cost is. So your input is X, your output is this whole expression. Okay, well, I think we're ready to go then. So now, what is C of 0? So what do? We write the function empty, plug in 0. This gives us something squared minus 10 something plus 27. And if you plug in 0, the best part about plugging in 0 is most of those terms go away. And we just have input 0, output 27. So how do we interpret that? First of all, what's one interpretation we immediately have? Oh, where did my drawing go? What's interpretation we immediately have of C of 0? What's any f of 0 going to represent? The y-intercept. So no matter what, C of 0, that's the y-intercept. F of 0, that's the y-intercept. Anything of 0, that's automatically the y-intercept. So we can immediately say this is the y-intercept. Right? That's one important interpretation. But now how do we actually read this in a complete sentence? What did this 0 represent? Yeah, so 0 thousands of pens. So 0,000 pens. So nothing. Right? If you make nothing, if you make no pens, so the company doesn't even open that day, you've made nothing. How much did that cost you? $2,700. $2,700, which is $2,700. Well, that's unfortunate, right? So you're the business owner, and you made no pens today, and it cost you $2,700. That's a bummer. Why did it cost you $2,700 to make nothing? Yeah, because no matter what, you're paying rent. No matter what, you're paying air conditioning. No matter what, you're paying electricity. There's all sorts of things you're paying for no matter what. So what could we call the $2,700? Well, yeah, that's true. You can call it a loss. You can also consider that your flat fee, right? That's your flat fee. Like no matter what, your cost of doing business that day, you got to pay the $2,700. Oh, I don't know if this is per day or if this is per month. It really doesn't clarify. But that really is your flat. No matter what, you're paying $2,700. I don't care if you make pens or not. But you have to pay that $2,700 for your operating costs, right? Okay. Well, so this one you can interpret using the units and making a complete sentence out of it. And we have the bonus interpretation that this was your y-intercept, which made it your flat fee, your operational cost. So as soon as you do a problem like C of 2, then this is just standard straightforward. You know, you plug in the 2, so it'd be 2 squared minus 10 times 2. Plus 27, so that's 4 minus 20 plus 27. So would that be 11? Okay, so C of 2 is 11. And I want you to notice, again, there's a lot of ways to write that. You could just write C of 2 equals 11. That's a valid way to write a final answer. And what does it mean? It means 2,000 pens cost $1,100. You know what's really interesting about that? What costs more, to make nothing or to make 2,000 pens? Yeah, I don't understand how that works exactly, that it actually costs you less to make something and costs you more to make nothing. Maybe the model is a little funny. Did I calculate that right?
Yeah.
Yeah, okay.
But that also makes sense because if you're thinking of the spending costs of the
Oh, okay. All right, yeah, that's a possibility. Okay, well, I think we're done, folks. I won't do the C of 5 with you. You can all do the C of 5 and then write down what it means. I would say my biggest takeaway for you is this process right here of actually labeling what the different parts of the function mean and represent words so that when you're all done plugging in your input and getting out your output, you can actually look at that and read it in English as opposed to just something that you wrote down. You know, even writing down a coordinate, that's nice and all. And putting it on the graph, that's nice and all. So I got a coordinate, there it is, it's 211. But being able to interpret it and say, oh yeah, that's 2,000 pens that cost $1,100. That's the most important part of the word problem. That'd be an interesting interpretation. It's called a word problem, not because it's written to you in words, but because they expect you to express the answer in words. That you're supposed to be able to express the answer in a complete sentence. Okay, so here we are, folks. Number 1.5, this is function arithmetic. This is a pretty straightforward section where you just take two different functions and you either add them together, subtract them together, multiply them together, divide them together. So there's not too much surprising that happens here. So they start you off by just giving you some definitions. And the definitions are important to the extent of knowing what that notation means. So I would write it down once in your own handwriting. Like, look at the very first one. It says, the way we're going to say f of x plus f of g is we're going to write down f plus g of x. So this is just the condensed notation. And you'd say f plus g of x is the same as just writing down f of x plus g of x. So you might say, well, why do we even have this notation? And maybe you can take a guess. Why do they have this notation? It's lazy, right? It just saves time. Instead of having to write x twice, you just write x once. And instead of writing 1, 2, 3, 4 parentheses, well, you still write 4 parentheses. But you have a savings there. You didn't have to write x twice. So that's it. This is just a condensed notation for saying add these two functions together. Likewise for f minus g of x, that's just the condensed notation for f of x minus g of x. And then when they say fg of x, that's just a condensed notation for f of x times g of x. And when they say parenthesis f over g of x, that's just a condensed notation for f of x divided by g of x. So this is just notation. Right? It's just notation. And you'll notice here, they even told us, what did they say about g of x? Provided g of x isn't equal to 0. Provided g of x doesn't equal 0, which we fully understand that now, that you can't allow an input to be 0 in the denominator. That's excluded from the domain. So this function is only valid when g of x isn't 0. If g of x was 0, this would be undefined and there would be no output. So it would not be a valid formula. Okay, so that's just notation. Looking ahead now, we have some examples here. What would be the best way to do these examples? In each case, they want us to take two functions and either add them or subtract them or multiply or divide. And then they're telling us a different number to input. So I'd like to show you that there's two ways to think about this. One way to think about it is to do each function separately and then either add or subtract or multiply or divide them. So let's try that first. What if we did it separately? We know that we want f plus g of 2, which by definition is f of 2 plus g of 2. So we could go ahead and feel free to just go ahead and go find f of 2, and then go find g of 2, and then add them together. So let's try that. So f of 2, I've got f of something equals 3x plus 1. And so I'll go ahead and plug in my 2. We're doing kind of some scratch work right here. And therefore, f of 2 is equal to 7. And then I could separately find g of 2. So g of something equals 4 minus something. So now again, I plug in 2. So g of 2 is 4 minus 2, which is simply 2. And now I have my two different answers that I need. I've got my f of 2, I've got my g of 2. I can go back now to my original problem and say f of 2 plus g of 2 is 7 plus 2, which is 9. So I imagine that some of you will like this method. You just calculate each one separately, and then after the fact, add them together. What's the other way of doing it? The other way is a little more formal, where you start by just saying, my function is f plus g of x, and so what I really need to do is add f of x plus g of x, in which case I would just write them both down one after the other. F of x is 3x plus 1, and g of x is 4 minus x, and then I would algebraically combine like terms and create my new function. So what do we have here? 3x plus minus 1x, that's 2x. And then 1 plus 4 is 5. now I have a new function. This is the function f plus g of x. It's just 2x plus 5. So this is the other way to look at the problem, is to actually come up with the function f plus g first, before you plug in any number at all. And now we'd say, f plus g, the function, is f plus g of x equals 2x plus 5. And now if I wrote that one empty, f plus g of something equals 2 something plus 5, what answer should I get if I plug in 2? Yeah, I mean, I better get 9, because I should get the same result that I got doing the other method. And in fact, 2 times 2 is 4 plus 5 is 9. So either way, you get the answer of 9. Would anyone like to weigh in on the power and pros and cons of these two different methods? What would someone say is the pro of this method? Yeah, maybe less errors, because you're doing simple computations one little bit at a time and only ever doing small computations. Okay.
Two answers and just add them together.
Yeah, you just get 2 simple answers and then add them together. Okay, what's the benefit of this method? Yeah, it simplifies the original expression itself, so that now I have this function f plus g of x, and now I have that function forever. And now I could answer this question for any other input. Like if now someone comes along and says, great, you answered for the input of 2, but now I'd also like you to do the input of 10, 11, 12, 13, 14, and 15. Then you wouldn't want to have to sit here and do this method over and over and over again. You would wish that you just had a function that you could plug in the numbers 10, 11, 12, 13, 14, 15. So if you have lots of inputs you're going to do, then there's a benefit to actually just finding out what that combined function is. But if you only had one to do, then maybe you would just do it this way. Yeah, just a thought. Okay, so there's adding 2 functions together. Now at this point you might say, okay, well, I mean, the rest of this is just going to be as straightforward, especially if you do this method, where you just find the answer separately, and then you either subtract them, or you multiply them, or you divide them. So what I'd like to do then is focus on the second method of how do you actually combine 2 functions together to create a new function. So let's take a look at part B. In part B, we're going to do f minus g of -1. So before we actually find that answer, let's find first f minus g of x. What is the actual function itself when you combine them? So again, by definition, f minus g of x is f of x minus g of x. And now what we're going to do is plug in the 2 functions, which, yeah, we're still doing number 1. So the first function, f of x, minus the second function, g of x, the first function is 3x plus 1. And the second function is 4 minus x. So we're actually just going to go ahead and combine those 2 functions together. Now, who'd like to tell me why I wrapped my 2 parts in parentheses? Because over here, you'll notice when I added f of x plus g of x, I just wrote them down. I didn't put parentheses. But now I am putting parentheses around both of them separately. Why did I do that? Why did I include parentheses this time? Yeah, because it's a minus. Minus is a whole different ballgame. Like, I want to subtract everything that's in here. I don't want to just subtract the first term. Notice how different it would have been if I had just written down 3x plus 1 minus 4 minus x. What would I be subtracting? Just the 4. Right? But technically speaking, if I subtract everything in here, what do I have to do with the minus? I have to distribute it. And so technically this answer is 3x plus 1 minus 4 minus a negative x, which is plus x. So it's very important that when you do a subtraction function, you definitely have to put parentheses around anything that you subtract, because otherwise you might forget to distribute the negative and then you'll get the wrong answer. Okay, so now combining like terms, we have 4x. And then 1 minus 4 is -3. And that's what f minus g of x is equal to. And now we can go back and actually solve the question that they asked us to solve, which was to plug in -1. So now I'll take my function and write it empty. F minus g of something equals 4 something minus 3. And I will plug in -1. And now I have my solution, which is -4 minus 3, which is -7. So f minus g of -1 is -7. And again, in and of itself, that doesn't seem all that interesting. But if you take it 2 steps further and say to yourself, well, this is my input-output, that means that on a graph, I have a coordinate at -1, -7. There we go. So I actually have a coordinate at -1, -7. So taking it that extra step puts this whole process in context by reminding you, okay, we're talking about a graph. We're talking about where that coordinate is on the graph. And that's the deep meaning of computing something like this. They're really saying, what's the location of that output on the graph? How is that? Does everyone feel okay about this so far? Any questions at all that you can ask? I'm sure that you've all done this before, so. How about the next one, part C? Kind of working backwards here. So f of g of the input 1/2. So again, at this point, you could just plug 1/2 into each function separately and then multiply the 2 answers. But I'd rather focus on doing the algebraic manipulation of the variable expressions. So we're going to do f of g. So f of g of x is really equal to f of x times g of x. And so when we plug in our 2 functions, once again, I'm going to use parentheses. So we're now saying that the first function was 3x plus 1, the second one was 4 minus x. And we're on our way to finding a general formula for f times g of x. What do we do now? And then we have 3x plus 1 times 4 minus x. Can we just leave it like that? Yeah, I mean, sometimes yes, sometimes no. Sometimes the problem wants you to leave it in factored form, and this is factored form. But sometimes they want you to multiply it together and get a quadratic, get an x squared plus something. And typically, if they're asking a problem like this, they want you to actually go ahead and FOIL it together. So let's go ahead and FOIL it together. Remember, FOIL, first, outer, inner, last. So we'll do first, so 3x times 4 is 12x. Outer, 3x times negative x is negative 3x squared. Inner, 1 times 4 is plus 4. And last, 1 times negative x is minus 1x. So we just did FOIL. We have all these terms. Now what do we do? And what does that mean to simplify it? Yeah, we definitely want to combine the 12x minus 1x. And then what else do we need to do? Yeah, we want to rewrite it. How?
11x minus 3x squared.
That's one possibility. There's kind of a standard way to express an answer if it has an x squared term. Which term should come first?
The x squared.
The x squared term. So we're going to have negative 3x squared, then the x term, then the number term. And the standard way of writing an answer is to go in decreasing powers of x. So this is x to the power of 2. What is this? X to the power of 1. And then technically there's an x right here. You don't see it, but there is an x right there. And that's x to the power of 0. So technically what we did is we do have x to the power of 2, x to the power of 1, x to the power of 0. It's in decreasing powers of x. But nobody ever writes x to the 0. But it is good to know that it is technically there. There is an x to the power of 0. But what's anything to the power of 0? Yeah, anything to the power of 0 is just 1. So there's really 4 times x to the power of 0, which is really 4 times 1, which is just 4, which is what the answer was to begin with. So it's just helpful to realize that anytime you have any number in the world, like the number, like, you know, how old are you? 27. You're really 27x to the 0. And there's always that little x to the 0 at the end of any constant, just, you know, in case that's helpful. Okay, so there we have it. That's our minus, or that's our, wait, we didn't even finish yet. Now what do we do? Now we plug in the half. So now we would have our FG, product FG of a half. I'm going to write it empty. Negative 3 something squared plus 11 something plus 4. And what we're now plugging in is 1/2. Now here's a good question. What's the best way to solve this now? Should you do it in your head? I mean, that's a little bit of a bummer to do all that in your head, or even by doing the fraction work. What would be the easiest way to do it? Yeah, use your calculator, folks. You're allowed to use calculators in this class. In fact, all math classes that you ever take for the rest of your life, you're allowed to use calculators. And so you can just plug that into your calculator. How do you plug this into your calculator? I'm going to write it down for you all. You would write negative 3 parenthesis 1 divided by 2 parenthesis to the power of 2 plus 11 parenthesis 1 divided by 2 parenthesis plus 4. So Might as well go ahead and try that on your TI right now to see that that's how you would type that expression in. The key is that you have to wrap your fractions in parentheses. That's always a rule. Anytime you type a fraction into a calculator, you want to wrap it in parentheses so that you're definitely calculating the right expression. A lot of times I see people type it in like this, where they say -3 times 1 divided by 2 squared, and that's going to be all wrong because there's no parentheses on the 1/2. Even writing +11 times 1 divided by 2, that's going to be all wrong. Well, actually, that will turn out to be correct by sheer dumb luck. And then, yeah, so my main message here is you have to use parentheses anytime you type in a fraction. Otherwise, you're gambling that your calculator is not going to tell you the right answer. So by the way, what's the answer? Is it 8 3/4? Did everyone get 8 3/4? 8.75? Okay. One last thing, did everyone get the decimal 8.75? I want to teach you a special button on your calculator, everybody. On your calculator, this is one of the best all-time buttons that I've ever seen on a calculator. If you're on your calculator screen right now, just go to that button called Math, which, by the way, is the most ridiculous button name of anything I've ever heard in my whole life. It's a button called Math. Like, what else would it be? It's calculator, right? So if you hit Math, what's the very first option? Frac, which stands for fraction. Which means now if you hit enter, and then it takes your number and says turn it into a fraction, hit enter again, and it will automatically turn the decimal answer you just had into a fractional answer. So what fractional answer did it give you?
35/4.
Yeah, 35/4. So 8.75 is really 35/4. And that's a really nice, powerful button that your calculator can take any decimal value and turn it into a fraction, provided it's a rational number, right? It can only turn a rational number into a fraction. It can't turn an irrational number into a fraction because by definition, an irrational number is not a fraction. Okay, we have one more to do from this section, and that would be the division one, right? Now, the division one is always kind of nice because there's not much to do. When I do G over F and solving that one in general, I'm just going to put a big division line there, a big fraction line, and then I just write down my two fractions. 3x plus 1. Oh, sorry. We want G over F, right? Yeah, so okay, so first I'm going to write down G of X over F of X, because that's the definition. And now I'll write down G was 4 minus X over 3x plus 1. There's not much to do with this. There's no simplification that we can do. That's just it. That's just the answer. So now we would say G over F of, I'm going to write 4 minus something over 3 something plus 1. Then we're plugging in -2. Now here, I'd really recommend that you do all this by hand, because you can just kind of plot along and say, okay, 4 minus -2, that's plus, so 4 plus 2 is 6. And then 3 times -2 is -6, so -6 plus 1. And so that gives me 6 over -5, and that's my answer, -6/5. But I know many of you would probably like to check your answer using your calculator. And so when you do, once again, I really want to implore you that anytime you type in a fraction, you need parentheses around it. But more importantly, if it's a complex fraction, like there's something in the numerator and there's something in the denominator, you need to wrap parentheses around the numerator first and then wrap parentheses around the denominator as well. So I want you all to appreciate, and go ahead and type it into your calculator, how you would type this into your calculator. It would look like this. You would say, first a parenthesis to say, here's my numerator, 4 minus, parenthesis -2, parenthesis, parenthesis, that's the end of my numerator, divide by, new parenthesis, here's my denominator, 3 parenthesis -2 parenthesis plus 1, end of denominator. So when you type a big fraction into your calculator, you need a whole separate extra set of parentheses to say, here's my numerator, and then here's a whole other extra set of parentheses to say, here's my denominator. Because the big mistake I often see is that people don't do those extra parentheses and they just write down something like 4 plus 2 divided by -6 plus 1. And that's all incorrect. Why is that incorrect? What is your calculator going to compute? It's going to do 2 divided by -6, which is the fraction -1/3. And then it's just going to go 4 plus -1/3 plus 1. So those parentheses are absolutely necessary to make sure that you're doing the numerator and then divide by the denominator. Okay? All right, did everyone else get the answer -6/5? Okay. All right, we're not going to do number 2, so you can cross that one out. It would work the same way, but you can just cross it out. Now, in our next section, again, it's asking you to add the function, subtract, multiply, or divide, and it gives you 2 pairs of functions. But here it says find the domain of the indicated function, and then find and simplify an expression for it. So you'll notice that no longer are they asking us to plug in an input, like 2 or -2 or 1/2. They just want us to find the function and then actually find the domain for it. So for the sake of class time, we already did a problem like number 5. These look just like the functions we just did. So let's cross out number 5 and go ahead and just do number 6. So let's do number 6. And we're going to create these functions and then write down the domain. All right. So again, we're doing number 6. So I'm going to write down my function so I don't forget. F of x equals x squared minus 4, g of x equals 3x plus 6. And let's start with a. In part A, we just want to add the 2 functions together. So everybody, you do that on your own. Go ahead and write down f plus g of x, which by definition is f of x plus g of x. And go ahead and write down those 2 functions, and then add them together, combine like terms, and write down the final expression. So checking your work, everybody would have had something like x squared minus 4, and then with or without the parentheses. Parentheses are always the best practice. So we have that, and you combine like terms. Did we all get x squared plus 3x plus 2? And then just as a bonus, can we factor that? What multiplies to make 2 that adds to make 3? You have 2 and 1, so we could say the final answer is x plus 2 times x plus 1. You'll notice the problem didn't ask you to do it. It just said to simplify. So x squared plus 3x plus 2 is pretty simplified. But whenever you can, if you can factor it, it's helpful to notice if you can factor it, say what it is. So now flexibly, we have 2 different possibilities for what the final answer could be. Okay, what about part B? We're going to do f minus g of x. So again, write down very carefully using parentheses what the difference of those 2 functions would be. Oh, domain. Should we go back? We should go back and do the domain right now. Folks, what is the domain of this? And remember, you always start by saying the domain is all real numbers except any input that would cause you to divide by 0. Will we ever divide by 0? No, there's no x in a denominator. Or square root of negative. And is there a square root expression? Yeah. No, well, there's a square, but not a square root. And so the domain is simply all real numbers. Because we're not excluding any numbers from the domain. There's, remember, when we talk about domain, the only thing you ever have to worry about is you're looking for a fraction with an x in the denominator. So this is what you're looking for when you look for a domain. You either look for a fraction with an x in the denominator, that's one thing to look at, or you look for a square root symbol with an x underneath it. So if you don't have a fraction with an x in the denominator, you're fine. If you don't have a square root with an x in it, you're fine. And in this particular case, we have neither one of those things, so the domain just stays all real numbers. You're not excluding anything. Okay, thanks for reminding me about that, Josh. Okay, so then in this case, we do need to use parentheses for sure. So f of x was x squared minus 4 minus g of x, which was 3x plus 6. And then you have to distribute that minus to both of them. So you really have x squared minus 4 minus 3x minus 6. And then when you simplify, do we get x squared minus 3x minus 10? Okay. And so what's the domain of that expression? It's still all real numbers. There's no fraction with an x in the denominator. There's no square root symbol. So the domain is all real numbers. Keep in mind that just because the domain is all real numbers, that doesn't mean the range is all real numbers. Right? Domain is left to right. And if you look at the graph x squared minus 3x minus 10, the function does indeed go left to infinity, and it goes right to infinity. But the range, how far down does the graph go? Only as far down as 12.25. Will it go up forever? Yeah, it will go up forever. So just to clarify, like with the problem that we just did, even though the domain was all real numbers, the range was only down as far as 12.25, and it went up to infinity. So the problem didn't ask us to do range. I'm just throwing that out there as a bonus. That you would have to take a look at the graph and consider the down up of the graph to say what the range would be. Even though with the domain, all you ever have to do is look for a fraction with an x in the denominator or look for a square root with an x underneath. The range, it's most helpful to just look at a graph and see how far down and up it goes. All right, then the product, part C. We'll find fg of x, which just means we're going to multiply f times x. So we have x squared minus 4 and 3x plus 6. So on the one hand, you can say, gosh, can't I just leave it like that? But oftentimes the problem does want you to go ahead and FOIL it together. So how would the FOIL work this time? First, what's x squared times 3x? Yeah, it is 3x cubed. Now, just in case that doesn't just come to you in inspiration, like you just know it, you can always write it down as x squared times 3x. And then walk yourself through it. Say, well, that's really x times 3 times x. And because you can move numbers around, I can call that 3 times x times x times x, which is 3x cubed. Right? So if you're not sure of what an expression is equal to, just take a moment, write it down, use the definition of what an exponent even is, and prove to yourself that it's 3x cubed. You know, don't just take a guess, but you know, just write down the steps. Okay, so we have 3x cubed, then outer, 6 times x squared, inner, negative 12x, and last, minus 24. So you can say that's the final answer, you know, by boiling it together. And now, by the way, did I write it in the right order? Yeah, that's x to the power of 3, x to the power of 2, x to the power of 1, x to the power of 0. So they are written in decreasing powers of x. On the other hand, what if they wanted the answer factored? That could be something else that we'll deal with, is factor the entire thing. Well, we don't have to start factoring this. We could begin at the beginning. Like 3x plus 6, what can I factor out of there? A 3. So already I know that part of my answer is just 3 outside of x plus 2. And then how do you factor x squared minus 4? Again, we haven't formally reviewed this in class yet. But do you remember the difference of squares formula? X squared minus 4 would be x minus 2, x plus 2. Right? So that's just a formula we have seen in the past. So now I can go ahead and take this whole thing. I already factored this part. Now the x squared minus 4 is x plus 2 times x minus 2. And now the whole thing is factored out. Although I could, since there's 2 x plus 2's, you can write it as 3 x plus 2 squared times x minus 2. Either of those would be really good answers. I don't mean to confuse you by throwing out too many options, right? This is definitely what they're looking for in this particular problem. But in other contexts, the problem would say factor this expression completely. And that's what this is. This is now that expression factored completely. And it's, as we get to, what, chapter 4, I think? In chapter 4, we talk a lot about factoring polynomials. There are benefits to having it written like this, and there are benefits to having it written like this. And it's important to be able to go back and forth between these two forms so that you can extract the information that you want. Okay, part D. It's just division. Oh, by the way, what's the domain? Still all real numbers, because there's no square root and there's no fraction, so it's all real numbers. So the domain is all real numbers. Does that mean the range is all real numbers? No. You'd have to graph that and see. So it's just fun. Let's graph it. What? Remember, one of the big questions we ask in here is, what does that look like? So we have a graph now of 3x cubed plus 6x squared minus 12x minus 24. There we go. So always in the back of our mind, anytime you look at any function, you should be asking yourself, I wonder what that looks like. Well, there you have it. That's what that looks like. So while I am saying it's a very important question to constantly ask, what does that look like? What does that look like? That doesn't mean to say that the answer is going to be interesting. But nevertheless, that is what the graph looks like. How far down does it go? Yeah, negative infinity. How far up does it go? Infinity. So in this case, the range is all real numbers. So in this particular case, the range is negative infinity to infinity. There we go. So just for fun, I'm going to write that down. This one, the range does happen to also be negative infinity to infinity. And how did we figure out the range? Yeah, by looking at the graph. Okay, last one, f divided by g of x. This is just dividing. So this is really f of x over g of x, which is x squared minus 4 all over 3x plus 6. Now something interesting does happen here. Again, we haven't formally covered factoring yet, but how can we factor the numerator? X squared minus 4 is really
X plus 2x.
Yeah, x plus 2x minus 2. And the denominator is really, and then as soon as you have that factored, what can you do on top and bottom? Yeah, you get to cancel out those x plus 2's, and you end up with something very simple, x minus 2 over 3. That's definitely a benefit. That's why it's important to learn how to factor, because you could be handed some expression that's very complex, and if you know how to factor and cancel, then you end up with something that's very, very simple. Now, at this point, we have to ask ourselves a question about what the domain is. So first of all, the domain is all real numbers except when you square root a negative. Do we have a square root? No, so we don't have to worry about that. Do we have an x in the denominator? Well, this is the tricky question. The original function, do we have an x in the denominator? Yes. So we would have to say, in the original function, you're not allowed to input a number that would cause you to divide by 0. So again, remember, when you do this, you circle the denominator, and you say, I want that denominator to not equal 0. So right now, we're finding our domain exclusion. Let's exclude whatever number that would cause 3x plus 6 equals 0. So that's really going to be 3x is not equal to negative 6. If you divide both sides by 3, we're saying x had better not equal negative 2. And whenever you find a domain exclusion, you should convince yourself that you didn't make a mistake. What happens if I plug in negative 2? 3 times negative 2 is negative 6, and negative 6 plus 6 is 0, so I just divided by 0. So for sure, x can't equal negative 2. And find the domain of the indicated function. This is the indicated function. So even though it does simplify into something where the domain is all real numbers, okay, the simplified one, the domain is all real numbers. But the original function, the domain is every number except negative 2. And so the interval notation for the domain here is actually 2 intervals combined with a union symbol, right? What are the two? Our domain would be the interval on the left and the interval on the right. So the domain would be from negative infinity to negative 2, union from negative 2 to infinity. And keep in mind what we're really saying. We're saying that for this function, f divided by g, okay, that function, not the simplified one, but this one, you can plug anything in the world that you want from these two intervals. You can plug in anything on the left, plug in anything on the right, and your calculator will actually generate an answer. So then what's up with the simplified expression? Because that might leave you feeling uneasy, a little anxiety. Well, like, well, what's the deal? I just simplified it. And the simplified answer, the domain is all real numbers, right? This, the answer is the domain is all real numbers. I can plug anything I want into this because there's no x in the denominator, there's no square root. I can plug anything I want into this, but apparently I can't plug -2 into this. So what's the truth? Anyone want to stab at that? The truth is that the indicated function, the original function, you can't plug in -2. The simplified function, you can plug in -2. So you just need to be specific about what you're saying. If somebody asks what's the domain, you'd say which one? The original or the simplified? And then finally, let's take a look at this because this is very interesting. What's the actual function? It was x squared minus 4 divided by 3x plus 6. So first of all, we're all wondering, hey, what does that look like? So what does it look like? What does it look like? I'm zooming out pretty far. Does it start to get curvy? So what's our graph? It's just a straight line, right? This is just a straight line. Furthermore, what is going on with this straight line at the x value of -2? Because we said -2 is not part of the domain. What do you think is going to be right there? Oh, do you see it? Boom. Boy, I can't. It's hard to get my mouse to stop right there. There we go. What's on the graph right there? Yeah, a little hole. There's a little hole in the graph, isn't there? There's a teeny tiny little hole. Meaning, is there a coordinate there? There is no coordinate there, which means -2 is not a valid input because there is no output. If you actually plug -2 into the original function, there would be no output. Your calculator would say error. Your calculator would say error, right? And that's why the hole shows up on the graph. But now watch this. What about the simplified expression? What's the simplified expression? X minus 2 over 3? How does the original graph compare with the simplified graph? There's the original, there's the simplified. There's the original, there's the simplified. There's the original, there's the simplified. What's the relationship between the two graphs? They're the same line. However, in the red graph, what was there at -2? A hole. In the blue graph, what is there at -2? A coordinate. There is no hole. If I can get my mouse to stop there. There is no hole in the blue graph. We fixed it. There it is. There is no hole in the blue graph. So this is a very interesting concept. The simplified graph does not have a hole. The original graph does have a hole. And that represents the fact that the domain had an exclusion. So just consider, what does it mean to simplify a graph? Or, I'm sorry, what does it mean to simplify an expression? The original expression had a domain exclusion, and on the graph there was a hole. The simplified graph has no domain exclusion, and there is no hole. So what did we do by crossing out these two x plus 2's? On the graph, what did we do?
Took out the hole.
We got rid of the hole. We filled in the hole, right? We put a coordinate in the hole. That's what happened. This is very interesting philosophically, right? The original function had a domain exclusion and a hole in the graph. By factoring and simplifying, this function does not have a domain exclusion. The domain is all real numbers, and we filled in the hole. So that's really interesting. On a graph, anytime you remove numbers because of a domain exclusion, what are you doing to your graph? You're making holes and removing chunks of it. Whereas if the function doesn't have a domain exclusion, there are no holes, and the whole graph is there. Okay, well, I know my phone just went off. I think now is a good time to stop. Now, there are a few more problems here that they gave us, and we might consider, and we might do one more of those just for fun. And then we'll move on to 1.6, which is really just taking a look at some various graphs. And then are we also scheduled for 1.7 today? I think we are. Okay, well, let's go ahead and take our break right now. Everybody take a break. The time is 9:02. Everyone will be back in the room at 9:12. All right, folks, let's keep going. I think the one we're going to do is number 7. What interesting thing is happening in number 7? Yeah, we have a square root. So there will actually be an opportunity to do a domain exclusion because we're square rooting a variable. Let me just switch that up. Come back, folks. All right. So let's walk our way through here. Now let's just focus on talking about the domain. Well, okay, we'll do that. We'll simplify it. We'll do the domain. So in number 7 then, what's the first thing we're going to do? Part A is add them together.
Yes.
So f plus g of x, I'm going to forego writing down all my steps and just write down the sum. X plus root x plus 1. Right? I mean, what other work is there really to show? We're just adding the two functions together. So what's our domain exclusion? We're saying we don't want to square root a negative. So how do we do this again? You circle the radicand, the part underneath the square root, and you say, we want what? We want x plus 1 to be, we don't want it to be negative. Therefore, we want it to be 0 or positive. So we say we want that to be greater than or equal to 0. So then we go ahead and solve. We subtract the 1 from both sides, and that tells us that x had better be greater than or equal to negative 1. So we draw our number line, we go to negative 1, we say it better be greater than or equal to negative 1. And so there's our domain. Now you notice what we found was the domain. We didn't find what to exclude from the domain. We found what the domain actually needs to be. Right? We're saying we're only allowed to include x values that would cause this thing to be greater than or equal to 0. So we're only allowed x values that are greater than or equal to negative 1. This is the domain. So we would say domain is from negative 1 to 50. Is part B any different? If we do f minus g of x, then we just have x minus root x plus 1. What's our domain now? Doesn't it? Yeah, there's a minus sign in front of the root, but does that matter? It doesn't matter at all, because what are we still interested in? That part. We're only interested in the part that's under the square root. Out in front there could be a party happening. I don't know what's happening out front, but inside I'm only allowed to square root positives and 0. So again, we would say I want x plus 1 to be greater than or equal to 0, and we end up with the exact same domain as before. So Jessica, does that minus sign matter? No. You might think it does, right? Just temporarily. But remember, we're just focused on what are we square rooting. We're not allowed to square root a negative. Okay, how about in part C? We're going to say fg, oh, I'm sorry, I should just write it down. So the domain is the exact same domain, negative 1 to infinity. So what about fg? So multiplying f times c, that gives us x times the square root of x minus 1. What's the domain now? Same thing. And what's happening inside the square root has not changed. We still need to make sure that we're only square rooting positives or 0. So we would still say x plus 1 had, oh, sorry, I wrote that down. There we go, x plus 1. So we still want x plus 1 to be greater than or equal to 0. We go through the same algebra and we find the domain still has to be from negative 1 to infinity. So our last one, f divided by g. Isn't that what they want us to do, f divided by g? Yeah, so now we have f divided by g. So now that's x over the square root of x plus 1. And now this becomes a little different, a little more interesting. Now, I erased my problem set here. The domain is all real numbers except for, and what are we looking for? We're looking for square roots with variables under it, and we're also looking for denominators with variables in it. So in this case, we have both. We have two concerns. So let's do one concern and then the other. Let's just stick with the square root concern first. So can we square root x plus 1 always? Not always. We need to first say that that x plus 1 had better be greater than or equal to 0. So that's 1/2 of the domain consideration. But then what else are we worried about? And what?
I can't put a square root.
Yeah, the entire denominator can't equal 0. That whole thing now, the entire denominator had better not equal 0. So now I'm saying take that whole thing, the whole denominator, and we're saying now separately the square root of x plus 1 had better not equal 0. And I want you all to notice these are the two separate statements that we're saying about what can and can't be for the function. On the one hand, we're saying the radicand had better be greater than or equal to 0. And on the other hand, we're saying the denominator had better not equal 0. So you'll notice then we looked at two different things, didn't we? On the one hand, we said the radicand better be positive or 0, and the whole square root had better not be equal to 0. So, you know, one way that would be nice to say that, well, you just write it in English so you have it for the rest of your life. On the one hand, you're saying radicand is greater than or equal to 0. On the other hand, you're saying denominator is not equal to 0. Those are really the two processes that you do over and over. Okay, so now let's piece all that together. On the one hand, we know that this means that x had better be greater than or equal to -1. So I'll start my number line at -1. I'm going to start here and move to the right. But now what is this information telling me? So remember, you do algebra with a not equal to symbol the same way you do algebra with an equal to symbol. So x is being added by 1 and square rooted. What do I do first? To get rid of the square root symbol. We square both sides. So now we know that x plus 1 had better not be equal to 0. And then we subtract the 1 from both sides, and we find out that x had better not be equal to -1. So we change that closed circle to an open circle. And now that is our domain. The domain is strictly everything to the right of -1. And so our domain is -1. And that's it. Now again, rolling around in the back of your mind, you might be asking yourself, what does that look like? So we could always go ahead and graph anything to see what it looks like. What was it? X divided by the square root of x plus 1. So what does that look like? We have a graph. It looks like this. And in terms of domain, where does the graph exist from left to right? So left to right. First of all, how far to the right does the graph go? Infinity. Now, how far to the left does it go? You'll notice how far to the left can it get? This is what's called an asymptote. It gets closer and closer, but never reaches. So does it ever go as far left as -1? No, it doesn't quite get there. It gets really, really close to -1, but it never actually gets there. If you looked at this graph, no matter how far up down you went, you're never going to get to a coordinate that actually says -1 comma something. So there is no coordinate at -1. You're approaching but never reaching. And that's why it's a parenthesis, and that's why it's an open circle. So what have we done here? We're basically talking about lots of different types of functions, and we're saying, what are you allowed to plug in? What are you not allowed to plug in? This is the biggest picture of what we're saying. We're creating functions. What numbers can you plug in? What numbers can't you plug in? And we're creating a mathematical language that allows us to communicate that to an audience. Okay, so you can cross out number 8. We won't do number 8. And we're ready to move on. Now this next section, 1.6, graphs of functions, it's basically just acquainting you with a family of functions. And maybe I should show you, there's this really cute meme, at least I would say it's a meme, of pictures of dancing functions, I think. Oh yeah, there we go. It's just a cute little pic that's out there on the internet. Here you go. It's somebody who took every different type of function and turned that function into the arms of some little person to make a fun way of depicting what graphs, generally speaking, look like. So like you can see the first function is just y equals x, that's a straight line, so the person just has their arm in a line. The next function is y equals x squared, which is a parabola, so they have their arms up in a parabola. And so on. And the whole idea is that there are families of functions, and it's important to know what each particular function looks like. I wonder if there's another one or a better one. I'd say that's probably it. Yeah. So anyway, have you ever seen that one? It's what?
It was on Reddit.
Oh, it's on Reddit, yeah. So it's kind of like the YMCA, except instead of the YMCA, it's math functions. So that's what this section is, section 1.6. It just wants you to be acquainted with what each of these things look like. Again, that's what we're always asking. What does that graph look like? So there's not much to say here. It's just acquaintance. So this first function, f of x equals a number. Well, what is the graph f of x equals a number? We've covered this. There's a formula. If I said f of x equals 6, for instance, what would that graph look like? Yeah, it's just a horizontal line, right? Because f of x is the same as y, and so we have y equals 6. This is simply the formula y equals b from y equals mx plus b, or y equals the y-intercept. So this simply represents a horizontal line going through whatever number they have there. And so they call this a constant function. F of x equals a number c. It's constant because no matter what you plug in for x, the answer is just going to be c. It's kind of a cute table of values. If I made a table of values where my function was f of x equals 6, then no matter what I plug in for x, what's y going to equal? Just 6. Right? And that's why they call it a constant function. Because the formula does not have an x, there's nothing to plug in, and so the answer is just 6, and we call it a constant function. And it looks like a horizontal straight line. Okay, so that one's called the constant function. This one's called the identity, because no matter what you plug in, that's the answer. That's also kind of a cute table of values. What if you made a table of values where your input is x, and the function is f of x equals x? Then whatever number I put in over here, what's my function equal to? The exact same thing. So they call that identity because x is equal to y. Now what is that function really? When I write down f of x equals x, it's really y equals x. And in terms of a function we know, this is really 1 over 1 x plus 0, which is mx plus b. So the identity function, which really just means the input is equal to the output, is actually a straight line whose slope is 1 and whose y-intercept is 0. Right? That's what they have drawn here. It's a line with the y-intercept of 0, and the slope is up 1, right 1, up 1, right. Now you notice they're also giving us the domain and range in these. So like over here, the domain, the constant function goes left to infinity, right to infinity, but the range is just a single number. Now they used brackets right there. It's not something I've ever seen before. Normally it's a curly bracket to just say you're just talking about the number 2. They're using brackets because brackets means included, but that's not an interval, that's just a single number. Maybe that's a typo, that should be bracket 2. Okay, what about the absolute value function? We don't all that often use the absolute value function, but just to make sure everyone sees it on Desmos, the absolute value function, which you can just type in by writing abs, there, is just what shape is an absolute value function? It's just a V. And you'll notice, what is it that everybody learns in grade school? What does absolute value do? Like if I took the absolute value of 5, the answer is 5. But if I took the absolute value of -5, the answer is still 5. A lot of people say an absolute value takes a negative number and makes it a positive number. It's not technically what it does, but that's the effect. And so compare the function of the absolute value of x compared to the function just x. What does absolute value do to the line y equals x? Yeah, it just takes that part down here, the negative portion of the line, and bends it upward so that it's positive. So that the absolute value function literally is still the line y equals x, but it turns all those negative values down here and makes them positive and bends it upwards to become the absolute value function. So the absolute value function is very, very much related to the identity function y equals x. Okay, turn the page, or I don't know if you have to turn the page, but these are just the rest of the various functions that we'll frequently deal with. You've got your quadratic, which is what we call parabola, your cubic function, and it's well worth noting that in a cubic function, how is a cubic function similar to a parabola? Like how would you describe the cubic function to a friend or an alien. What does it do? Like if you're going to tell somebody to draw this, but you're talking over the phone, you're like, okay, go to the origin, all right, then what? What do I draw to the right? A parabola to the right. Now what do I draw to the left? Exactly, a parabola facing down. Now technically it's a cubic, not a parabola, so it's not technically a parabola going up and a parabola going down, but that's what it looks like. You have something that looks like a parabola facing up, and it looks like a parabola facing down. So that's your cubic graph, essentially what it looks like. Now, then you have, instead of x squared and x cubed, you have square root x and cube root x. How is the function, how is the graph of the square root of x related to the graph of the square of x? Compare those two. What's going on there? How do you get this graph from that graph? It involves looking at the top graph and then turning your head 90 degrees. What are we technically doing with our parabola to generate the square root graph? Yeah, you just take it and turn it sideways, right? 90 degrees. So if you take the parabola, let me draw it over here. If I take this parabola, this part anyway, and I tilt it 90 degrees, it becomes the square root function. So the square root function really is just the parabola rotated to the right 90 degrees. What about the cubic graph? Almost the same thing, right? You've got that graph and it tilted, but it also flipped. The key is that they're related, that you can generate the cube root graph by manipulating the cubic graph and flipping it and rotating it in different ways. Okay, and then finally we have this graph called the reciprocal graph, 1 over x, and or 1 over x squared. And we will cover these functions when we get, I think, to chapter 5. Well, that's really all there is to say in this section. They just want us to be familiar with the fact that there are certain graphs that we see time and time again, and they want you to generally be comfortable with recognizing them visually. So like if you were just walking down the street and there was a billboard and you saw this graph right here, you could turn to your friend and say, hey, that looks like the reciprocal graph, 1 over x. Or you're driving down the street and you see this, you're like, hey, that looks like a cubic. Or you're driving down the street and you see this, you're like, hey, I think that's the square root function. And I think that's it. I think even the homework for that section, you're just recognizing and matching up this graph is this and this graph is this. Okay. Everyone, let's turn on this next page here. So up at the top, it gives us a definition. It says zeros of a function. Now, first of all, what does the word zero mean? Nothing, right? It means zero. It means you have 0 slices of pizza for breakfast, you have $0 in your pocket. 0 just means 0. But in the context of working with functions, 0 actually has another meaning. It says the zeros of a function f are the solutions of the equation f of x equals 0. In other words, x is a 0 of f if and only if x comma 0 is an x-intercept of the graph y equals f of x. That's a lot. That's a mouthful. But go ahead, right up there, right next to that gray box. Everybody write this down with me. That when we have our x and y axis, and we have some sort of function, that on the one hand, we know that the y-intercept is equal to f of 0. And on the other hand, we know that these points right here are called x-intercepts. And an x-intercept, there are many synonyms for x-intercept. You could either call this an x-intercept, or you could call it a root. That is another historical word. It means it's the root of the equation. It's the number that you plug into the function to make it equal 0. Oh, and by the way, the x-intercept is when f of x equals 0. So you can either call it an x-intercept, you can call it a root, you can call it a solution, or you can also call it a 0. And what they mean by that is the x-intercept is when the function takes on the value of 0. So when we say that a particular x value is a 0 of the function, it means if you plug that number into the function, it zeroes the function out. So for instance, take the simple function x squared minus 4. If I were to say, what is the x-intercept of that graph? I'm going to go ahead and do this real quick. This is what my parabola looks like. So in context, I could go ahead and say, here's my function. What are the x-intercepts? The x-intercepts are 2 and -2. Right? That's one way I could say it. I could also say, what are the roots of this equation? The roots of this equation are x equals 2 and -2. I could also say, what are the solutions to x squared minus 4 equals 0? So if I want the solutions of x squared minus 4 equals 0, that is taking f of x and setting it equal to 0, then again, I'd do a little algebra. I'd say x squared is equal to 4, square root both sides, x is equal to 2 or -2. Those are the solutions. The word solution always means in context, set the function equal to 0 and solve using algebra. So 2 and -2 are the x-intercepts, 2 and -2 are the roots, 2 and -2 are the solutions to the function equal to 0. And then finally, you could just say x equals 2 and -2 are the zeros of the function, because if I do f of 2, that becomes 2 squared minus 4, which is 4 minus 4, which is 0. So the function takes on the value of 0. If I do f of -2, then -2 squared minus 4 is 4 minus 4, which is 0. So 2 and -2 are the only numbers I can plug into this function that would zero out the function. That is, make the function equal to 0. Yep. So what do we have here? 4 words, zeros, solutions, roots, and x-intercepts that all mean the same thing. To which you might say, what the heck? Why do we have 4 different ways of referring to the same thing? And it's because mathematics was developed over a long period of time by lots of different mathematicians in lots of different countries, and people ended up calling them by different names. The end-all be-all of what we're talking about is, again, with any given function, you can do one of 2 activities. So if you have a function, you can do one of 2 activities. You can plug something into the function, or you can set the function equal to something. And the most common number to plug in or set equal to is 0. And so the main activity that we do in algebra is take a function, set it equal to 0, and solve. And so this takes on a lot of special names because it's what mathematicians have been doing all along. So you can either, when you set f of x equal to 0, you can call the solution an x-intercept, a root, a solution, or a 0. Okay, that's it. That's the vocabulary portion of the lesson. All those words mean the same thing. So now what do they want us to do? Is it for me? No. The x-intercepts of a graph go by the following names: root, 0, and solution. Now it says graph the given function, state the domain, state the intercepts, and test for symmetry. See that phrase, test for symmetry? You can cross that out. We're not doing test for symmetry. Now, they're about to ask us to do an activity that we did do the other day. I feel like we already did a couple of these the other day where they gave us a function and we found the y-intercept and the x-intercept, and then we tried to draw a graph through it. So this is kind of more of the same. The only difference is they're asking you to do everything. They want you to take this function, say what the domain is, find the y-intercept, find the x-intercept, and try to build a graph. So let's just do, well, goodness. I want to do a lot of them with you, but I also want to have time for other things. Oh, what the heck? Let's just go for it. So, okay, so number 1. Let's go in order, shall we? We're going to go in the order of y-intercept, x-intercept, domain. So number 1, we have the function x minus 2 over 3. So what's the y-intercept? What do? You just plug in 0. So that would give us 0 minus 2 over 3, which is just negative 2/3. So that's our y-intercept. How do you find the x-intercept? Yeah, you set f of x equal to 0. And I'm always going to write f of x equals 0 first to remind me what I'm about to do. Then I'll substitute in what f of x is. It's x minus 2 over 3. And then how do we do algebra here? X is being subtracted by 2 and divided by 3. So what do we do next? We multiply 3 both sides so that the 3's over here cancel. Now you have x minus 2 is equal to 0. X is being subtracted by 2, so you add by 2 and you get x equals 2. So let's look at this number in context. What are we saying about the number x equals 2? First of all, we're saying that the x-intercept is at 2. Right? That's our x-intercept. we're also saying that 2 is the solution to this equation. Right? So 2 is the solution of setting the function equal to 0. We're also saying that 2 is a 0 of the function, because if I plug 2 into this function, I'll get 0 as an answer. If I plug 2 in right here, 2 minus 2 is 0, 0 divided by 3 is 0. And so indeed, 2 is a 0 of the function, because if I plug in 2, it'll equal 0. And what's the last thing? Oh yes, 2 is a root. Root is just another word that means the same thing. And what's the domain? The domain is all real numbers except, do I have an x in the denominator? No. Keep in mind, it's not just a denominator that you have to worry about. It's only a denominator that has an x in it. And we don't have a denominator with an x in it, so we don't have to worry about that. Do we have a square root? No. So the domain is just negative infinity to infinity. All real numbers, you can plug anything you want into there. So then what? On my graph, the y-intercept was negative 2/3, so that would be right about there. And we know that this is a straight line because there's just a single x value. This is really 1x minus 2 all over 3, which is really 1/3 x minus 2/3. And so by mx plus b, we now know that the y-intercept is negative 2/3, which we already found, and the slope is up 1, right 3, up 1, right 3. So our graph looks like that. And so is the domain really left to infinity, right to infinity? Yeah. So let's try the next one, number 2. Now, I'm standing up here thinking to myself, I swear we just did this the other day. Didn't we do something like this just the other day? I really feel like we did. I don't want to waste our time by spending time doing examples that we don't need to do. But on the other hand, I don't want to leave you high and dry. If there's a question like this on the homework, I want to make sure I've done it with you so you feel prepared. So how about we'll just do 2 more of these. So we have our function f of x equals 4 minus x squared. So again, let's just go through the procedure. What's our y-intercept? You just plug in 0. So that'd be 4 minus 0 squared, which is just 4 minus 0, which is 4. So our y-intercept is 4. And then how do you find the x-intercept? You set f of x equal to 0. So I say 4 minus x squared is equal to 0. Now notice, for the most part, the way we do algebra, we keep x on the left and we move everything over to the right. Are you allowed to move x squared to the right? Sure you are. It's a little non-traditional, but it might be easier just to go ahead and move the x squared over to the right, because then we automatically have 4 equals x squared, and then x is being squared, so you can square root both sides, and you have x is equal to plus or minus 2. Remember, anytime you do a square root in the process of algebra, it's a plus or minus. So now we have 2 different x-intercepts at plus or minus 2. Let's go ahead and make our graph then. Our y-intercept was at 4, and our x-intercepts were at plus or minus 2. And we know it's a parabola, we know it's facing down, and so you can pretty much see your parabola now. Look like that. And what is our domain? Do we have an x in the denominator? No. Do we have a square root? No. So the domain is all real numbers. Okay, let's do number 3. Number 3 is fun. And it predicts some material that we're going to get to later on. Okay, so in number 3, come over here, we have f of x equals x times x minus 1 times x plus 2. Now you're probably all wondering, what does that look like? Were you all wondering that? You're sitting there, you're about to raise your hand. Mr. Sheep, what does that look like? So let's see what it looks like. And it looks like x times x minus 1 times x plus 2. And so, what does it look like? What family function would that be? What did someone say?
Is it cubed?
It is a cubic. And other than the fact that it goes up to the right and down to the left, I realize it has a little wiggly in the middle there. But it is a cubic, and how do we know that anyway? Because what?
Because it has to do.
Yeah, if you multiply this whole thing out, like start by foiling this would be x squared minus 1x plus 2x minus 2. Then if I multiplied in the x all the way through that, I'd have x cubed minus 1x squared plus 2x squared minus 2x. And so I'd have x cubed plus 1x squared minus 2x. And that would be my function. And therefore, yes, it is a cubic. Right? You didn't have to write all that. But yes, this is a cubic graph. That's the family that it would fall under. The most simple way of knowing that is not by doing all that FOIL work, but by just saying, well, I have an x times an x times an x. That's x cubed. I know there's other things going on in there. But once you multiply the whole thing together, you would have x cubed. Okay, so we have, generally speaking, a cubic. What's our y-intercept? Yeah, so everyone go ahead and plug in 0. Now, we have 3 parts here, right? I'm going to wrap this x in parentheses. What I really have is something times something times something, right? And I want to plug in 0. So this becomes 0. That becomes 0 minus 1. And this becomes 0 plus 2. And if you multiply all that together, you get 0, right? 0 times negative 1 times 2, anything times 0. So there's our y-intercept. Now what about the x-intercept? This is the exciting one. So to find the x-intercept, you set the function equal to 0. And the function happens to be x times x minus 1 times x plus 2. And at first glance, you might not know how to solve this. Like, oh, that looks a little different from anything I normally solve. But this is the best situation in mathematics is when you have something times something times something, because then you can use the 0 product rule. What does the 0 product rule state? That what? Yeah, that if you have something times something times something equals 0, that means one of them has to equal 0. One of them has to. If you have 3 numbers multiplying to equal 0, one of them had better be 0. So you get to set each of these equal to 0 and say, well, either that means x is 0, or that means x minus 1 is 0, or that means x plus 2 is 0. One of those has to be true. And so your situations are x could be 0, or x could be 1, or x could be negative 2. And those are your x-intercepts, or your roots, or your solutions, or your zeros. All those words mean the same thing. Furthermore, I've got my graph up here still. Where are the x-intercepts? There's an x-intercept at 1, at 0, and negative 2. And those are the x-intercepts we just found. Yeah, 0, 1, or negative 2. And finally, what's the domain? How far to the left does the graph go? And we'll sketch it real quick. We have an x-intercept at negative 2, at 0, and at 1. And it goes like this, like that. So how far to the left will it go? Infinity. And how far to the right will it go? Infinity. So the domain is negative infinity to infinity. Okay. I feel like we've already solved a problem like number 4, so you can just scratch it out. All right. So folks, at this point, I almost feel worried that I've bored you. Now, of course, that's not possible, right? In a math class, you're never bored. But like, maybe at this point, you're like, we get it. Y-intercept, you plug in 0. X-intercept, you set it equal to 0. Domain, left to right, find your domain exclusions. I feel like we've really hammered these concepts hard over the last couple of days. I hope you don't feel like I'm beating you over the head with it. Or maybe you feel like, great, this was good. Like, that was a good amount of practice. Now we're ready to move on. So let's take a look then. Our next problem is this full page of information. This is one problem. We're going to look at that graph, and we're going to answer everything. I really like this problem because it kind of shows you all the different ways that you can talk about a function. I wish that there was some way for me to project this onto the whiteboard. Well, I suppose I could temporarily, because that might help us write all the answers down together. So maybe I'll do that. Let's see if I can do it. I'm just gonna, well, no, that'd be tricky. Don't mind me. Just a little quick parkour there. All right. Okay, it's booting up. So start by looking at the definitions up at the top, folks. It says general function behavior. The first word is increasing. That a function increases. Now you read the whole definition that says the function values increase as the inputs increase. Really what they're meaning is that if it increases, the graph is going like this, up and to the right, right? So we might as well just draw little sketches so that we all know what we're talking about. A function is increasing if it's going like this. Likewise, a function is decreasing if it's going like this. And a function is constant if it goes straight across. So we use the word increasing, decreasing, and constant synonymously with what we meant originally by the slope is positive, the slope is negative, and the slope is 0. Right, so those terms all mean the same thing. A local maximum is a point where the function changes from increasing to decreasing. Well, if a function is going from increasing to decreasing, it looks like that. It was increasing, and then it stopped, and it started decreasing, and the maximum is the point at the top. Right, so that's your max. Likewise, the local minimum is a point when the function changes from decreasing to increasing. So my function was going down, and then it started going up again. And so that's my minimum. A local extrema is just all your maximums and minimums. So we use the word local extrema to mean maxes and mins. Maxes and mins. Okay. All right. So that's just some vocabulary, so we're all using our words the same way. So now let's start. What's the domain of this function? So this is the function we're looking at. First of all, are there any holes? No, that was kind of nice of them, right? So what is the domain? How far to the left does the graph go, and how far to the right does it go? Yeah, is it just -5 to 3? Now what's the range? How far down does the graph go, and then how far up does the graph go? It goes down as far as -5, and it goes up as far as 4. Now notice, the graph exists in many places. Like you might say, well, but what about that point? There, the graph is only going up as far as 3. But globally, overall, the entire graph goes up as far as 4. So that's definitely the range. Determine f of -2. So what is f of -2? This is kind of how we started class. What does this mean? What are we plugging in? -2, and therefore -2 is the x value, right? We're plugging in an x value, so that means go to -2, and then go to the coordinate. So there's the coordinate. And therefore, f of -2 is equal to 2. Again, input, output, right? That always just represents a coordinate. Another way of looking at that is they said, where's the coordinate that begins -2? That's how else they could have asked that question. Instead of saying f of -2, they could have said, where's the coordinate that begins with that -2? And where is the coordinate that begins with a -2? Right there. -2, 2. And therefore, f of -2 is equal to 2. Now, notice here, this is kind of like the forward direction. You plug in a number, you see what the output is. So I went to -2 on the x-axis, and then I found the output on the y-axis. This is going to go backwards. Here, they're telling us the output. They're telling us the output is 4. So what is the input? So when is the output 4? Only right there. That's the only coordinate on the graph whose output is 4. And so what was the input? -3. So they're saying x is -3. That's what they're asking us to find. Find the x value whose output is 4. And so the only point on the graph whose output is 4, is the coordinate where x is equal to -3. So the answer there is x equals -3. Notice this is subtle. When they say solve f of x equals 4, remember that means algebra, you're solving for x. And so we're saying x is equal to -3. Whereas here, they were saying just plug in a number, and so the answer was simply equals 2. So it's a little bit. Okay, how many x-intercepts do we have?
3.
We've got 3 of them. And so you'd say x int colon x is equal to -4, -1, and 1. And then it says list the y-intercepts. Where's the y-intercept? Just at -1. So the y-intercept is -1. Can you have more than one x-intercept? Yeah. Can you have no x-intercepts? Should I have a graph that looks like this? Should I have a graph that looks like this? Yeah, so it's possible to have no x-intercepts. It's possible to have one x-intercept if it was just a line. That's one x-intercept. So x-intercepts, you can have none, you can have 1, you can have 3, you can have 10. X-intercepts can come in any variety. Whereas y-intercepts, can you have no y-intercepts? Well, again, yes, you can. Like this one doesn't intercept the y-axis. Can you have one y-intercept? Certainly. Can you have two y-intercepts? Could you have a graph that intersects the y-axis 3 times or 2 times? It's not a function. It fails the vertical line test. So at most, you'll have one y-intercept. Y-intercepts, you'll either 0 or 1. That's it. Whereas x-intercepts, you can have as many as you like or as few as you like. Okay, find the zeros of f. What does that mean? What does 0 mean again? It's just the x-intercepts. We already answered this question. These are the x-intercepts, these are the zeros. The zeros are x equals -4, -1, and 1. Because if I plug -4, -1, or 1 into that function, the answer will be 0. The coordinate would be 0. Now this next question, solve f of x is greater than or equal to 0. When is the function greater than or equal to 0? And let's remember again what f of x is synonymous with. F of x is synonymous with y. When is the y coordinate? So either when is the y coordinate 0 or when is the y coordinate positive? Well, what does that look like on the graph? When we say we want the function to be greater than or equal to 0, what are we really saying? What part of the graph are we interested in? Yeah, the part that's above the x-axis. Everyone take a look and watch and note that what I just drew is when the function is greater than or equal to 0. And maybe you want to sketch that yourself and say this, all this part above, so f of x greater than or equal to 0 means the graph is above the x-axis. Now keep in mind by the word above, I'm being a little flexible there. It either means above or on the x-axis or strictly above. What? Above or on. What if I wanted to only look strictly when it was above the x-axis? What if I wanted to turn all those into open circles? Then what would I be asking? That would be f of x strictly greater than 0. Right, does that make sense, the difference? That if I were to say, when is f of x strictly greater than 0, I would knock out those points on the x-axis and put open circles there. Because I don't want to know when the function is equal to 0 on the x-axis. I just want to know when is the function strictly greater than 0. So with the open circles, that would be f of x is greater than 0. With the closed circles, that would be f of x is greater than or equal to 0. Right, so f of x greater than 0 means strictly above. This is a question we'll come back to many, many times, is they'll ask us to solve when is f of x greater than 0 or when is f of x less than 0? What does that question mean? F of x is less than 0. Then what are we interested in? What would f of x less than 0 mean? Everything below the axis, everything below the x-axis. So then that would be the portions of the graph where f of x is less than 0. And that just means below the x-axis. So I'm kind of throwing in some extra definitions here that go beyond the question that we're on. What question were we on? Number 8. Solve f of x is greater than or equal to 0. So now that we've kind of talked about what that even means, how do we give the answer? When is the graph on or above the x-axis? They're asking for the answer in interval notation. That's not obvious, but they are. So along the x-axis, let's just look at the red part now. When is it greater than or equal to? So when is the graph above the x-axis? Between -4 and -1, and then again between 1 and 3. So our answer would be from -4 to -1, union from 1 to 3. And you'll notice that I use brackets. Why did I use brackets? Yeah, because those are closed circles. They actually do get to -4 to -1 to 1 and 3. Isn't it just wild how much meaning there is in some simple little statement? To just say solve f of x is greater than or equal to 0 means a lot. It means when is the graph above the x-axis or equal to the x-axis? And what it really means is what x values can I plug in such that the y-coordinate will be positive or 0? So what x values can I plug in? These x values. I can plug in any x value from here, and then the function would either be greater than 0, meaning above the x-axis, or it would be equal to 0, meaning it's a solution. Okay. Find the number of solutions to f of x equals 1. So what does that mean? F of x is equal to 1. F of x is synonymous with y. So they're saying which coordinates have a y value of 1. So which coordinates on the graph have a y value of 1? There's a few, huh? That one, that one, that one, and that one. So how many solutions are there to f of x equals 1? 4. They didn't ask us to actually find it. They just said how many are there. There are 4 solutions. In other words, there are 4 coordinates on the graph whose y value is equal to 1. Everyone can cross out the number 10 because we're not talking about even odd and neither. By the way, you can stop me at any time. I don't mean permanently and go home. I mean questions. So, we're just kind of plodding along through these, but does anyone want to ask a question right now? Because maybe I've already passed your question. You're like, man, I had a question back on number 5. Anybody want to clarify before we keep going? Okay. All right, well, let's try the next one. Number 11. List the intervals. Again, interval means interval notation, where f is increasing. So I'm going to go back to my graph and do a new color coding. When is the graph increasing? From here to here, and from here to here. Does everyone agree that's where the graph is increasing? So we just need those intervals. So what's the first interval where it's increasing? From -5 to -3. Where's the second interval? From 0 to 2. So that's it. The interval where it's increasing is from, oh gosh, -5 to -3. And then again, union from 0 to 2. Whenever you look at interval notation, you want to say to yourself, okay, we're talking about x values. We're saying choose any x value from this interval, and the graph at that moment will be increasing with a positive slope. All right? So if you choose any x value from this interval, and you go look at the graph, at that moment, the slope would be positive and the graph would be increasing. What about the next one? List the intervals where f is decreasing. So where is it decreasing? From here to here, and from here to here. And so what intervals are those? It's decreasing from the -3 to 0, and it's decreasing again from 2 to 3. So we'd say from -3 to 0, union 2 to 3. Okey-doke. Now, a philosophical caveat. Is that the right word? Use the word caveat? A caveat is like an exception. Like, let's think carefully about this. Should this be a bracket or a parenthesis? Is it technically decreasing right there at that point? At the very tippy top, what's the slope? If you look at the top, like right here, we all agree the slope is negative. And right here, we all agree the slope is positive. What's the slope at the top? If you're at the very top, are you currently increasing or decreasing? Or neither? Probably neither. So what do you think? Do you think maybe that we should go back and say strictly decreasing, all of those should be parentheses? What do you think? Because are you technically decreasing or increasing at a point that's a maximum or a minimum? This is something that I would consider philosophically open because I see different textbooks define it in different ways. So I've seen some textbooks put brackets there and some other ones put parentheses there. It's a tough one because technically there is no slope at the top. It's not positive or negative. So I only throw that out to you as a suggestion that if when you go to type it into the more system, maybe the more system wants the parentheses here, maybe the more system wants the brackets there. I forget off the top of my head. But let's just be open to the fact that different textbooks interpret that in different ways. So that when you go to type it in, if you're like, oh, what the heck, it's telling me my answer's wrong. Maybe try changing the brackets to parentheses and seeing if maybe that's what they're talking about. Does that seem weird to think that there's disagreement in a mathematical community about how to say certain things? It's just some subtle philosophical difference that mathematicians might have with each other. Okay, so what are the local maximums? Where's the tippy tops of the graph? Here's one, and here's one. Now, how do we give a maximum? We list coordinates. So this is not interval notation. Here they want the actual coordinate. So one maximum is at the coordinate -3, 4. And then another coordinate, or another maximum is at the coordinate 2, 3. Now again, depending on how the textbook asks the question. Maybe they say, find the x values where there is a maximum. In which case you say, there is a maximum, there is a max at x equals -3 and 2. So that's another way that a textbook might ask for the question. They're saying, where is the maximums? When x equals -3, there's a maximum. When x equals 2, there's a maximum. So again, there's different ways books and software programs will ask for an answer. It could either be list the coordinate or it could be list the x values. Same thing goes for the local minimum. So where's our minimum? Here and here. These are two low points. That's a low point, that's a low point. So one minimum would be the coordinate -5, -5, and the other one would be at the coordinate 0, -1, or they could be meaning just list the x values. There's a minimum at x equals -5 and it's 0. And then you notice the very last question is 15 and 16. They're distinguishing now for the absolute maximum. Find the maximum point on the graph, and then find the minimum point on the graph. So what's the absolute highest point on the graph? Sorry, the absolute highest point? Yeah, -3, 4. That's the absolute highest point on the graph. And then the absolute lowest point on the graph is -5, -5. Now again, here a textbook or an author might say, no, I mean the function. What's the largest value the function takes? And what is the largest value the function takes? 4. So they could be saying the maximum of f of x is 4. That'd be another way you could say it. That the function itself, the largest possible value, the largest possible output you're going to get out of it is 4. Whereas the smallest possible value that you're going to get out of it, min of f of x, the smallest possible value is -5. Now, right now, you might be looking at everything that we just wrote down, and you're like saying, oh man, Mr. G, there's a lot of different ways to write answers. What's the right way? There's not always just one right way to say something. You know, it's just like writing an essay. There's a lot of different ways. If I asked all of you to write a simple essay on whether or not we should have stop signs in the parking lot, you could write that essay in lots and lots of different ways, and they'd all be valid. And likewise, there's a lot of different ways to answer a question. It all boils down to how the question was asked. Yep. All right. So what are we down to? There was, these are some nice questions right here. These are some graphical questions. Keep in mind that a graph is the function. The function is the graph, and the graph is the function. The graph is just a visual interpretation of the function itself. All right. So what do we have here? We have use the graphs of f of x and g of x. So over here we have the function f of x, and over here we have the function g of x. And they labeled them. This is the function f of x, that's g of x. And they're asking, add the functions together when x is 1, subtract the functions together when x is 2, multiply the functions together when x is 2, and divide the functions together when x is 4. So what do we do? Like, let's take a look at this one. What do we do? What's the definition of f plus g? This is just f of 1 plus g of 1. Right, because that's the notation they use, but this is really what they mean. So what's f of 1? Yeah, if you look at the x value of 1 and you go up, the coordinate is 2. So x input is 1, y output is 2, so that's just 2. And then what's g of 1? Always when you interpret a function, g of 1, you go to the x-axis for 1, and you just go until you find the coordinate, and the output is 3. And so in this particular case, the answer is just 5. Say that the key here is when you read a graph, you start on the x-axis, and then you go up or down to find the y-intercept, or to find the y value. You start with the x value, and then you go look for the y value. So when I have g of 2 minus f of 2, first we find g of 2. So I go to my g graph, I go to x is 2, I look up to find the coordinate, that has an output of 3. And then f of 2, I go to my f graph, I do an input of 2, I look up to find my coordinate, and the output is a 3. And so 3 minus 3 is 0. Nothing tricky that we're doing here. It's just reading the graph. You know, one thing that's very helpful is to think of relabeling your x and y axis as input and output. If you relabel your axes as input output, that helps you in keeping in mind what we're even doing here. Like fg of 2, that's going to be f of 2 times g of 2. So my input is 2. So I go to my f graph, my input's 2, my output is 3. And then I go to the g graph, my input is 2, my output is 3. And so in this case, I get 9. So everybody go and try that last one. Find f of 4 divided by g of 4. Really nice notes, folks. Okay, so you have f of 4 divided by g of 4. And f of 4 is what?
0.
Yeah, just 0. So if you input 4, the output is 0. So f of 4 is 0. Over g of 4. Now at this point, you might say, it doesn't matter. I don't even have to find g of 4. My answer is already 0, right? Are we guaranteed that the answer is going to be 0? What can I put here that the answer wouldn't be 0?
0.
0. If g of 4 was also 0, the answer would not be 0. The answer would be undefined. So we do have to actually finish the problem to make sure that g of 4 is not also 0. So g of 4, if I plug in 4, g of 4 is 4. Okay, so it is fine, and 0 divided by 4 really is 0. Okay. Any questions? Any thoughts? Any feelings? I bet you're all feeling like I'm feeling, which is, thank goodness we still have 40 minutes, right? I find that I'm always excited when there's a lot of time left. I'm like, yes, there's a ton of time left. And students are like, why would you be grateful for that? Okay, so this last section is called graph transformations. And right there at the top, there's this large gray area where they give you lots and lots of essentially formulas to tell you what something means or is. And, well, it's kind of working out to have this right here. What I'd like to do is demo all of these for you on Desmos so you can see where all those formulas come from. And hopefully it makes it a little more sense as well. So, maybe I will turn that back on. So, let's start with the idea. So first of all, a graph transformation means to go back to the idea of these parent functions, like the identity, the absolute value, a quadratic, a cubic, a square root, a cube root, a reciprocal, and the reciprocal squared. What you can do is take all of those and just move them around a graph. What does it look like that? Is it still booting up? It is still booting up. No, that's not what I meant. All right, we'll just leave it like that. So let's all say that we start with the parent function x squared. So there's our parent graph. And yeah, that's fine. So there's our parabola, and I'd like to know, how can I move that parabola around the graph? So right now I just have f of x equals x squared. And my parabola starts at the origin, and it looks like this. But what I'd like to know how to do is, how can I take my parabola, move it up and down? How can I take my parabola and move it left and right? And how can I take my parabola and make it taller and skinnier, or wider and larger? Or how can I take my parabola and flip it upside down? Those are all the basic questions I want to ask, right? So taking my parabola, how do I move it up or down? How do I move it right or left? How do I flip it upside down? How do I make it taller and skinnier, or wider? And those are all the basic questions. How do I do it on the function? So you might already know some of those off the top of your head. So let's just go in order from the list. And the first thing they talk about is moving the parabola up and down. So what if I take my x squared and I start adding a number to it, like +1, +2, +3, +4? What's happening to the graph? Yeah, it's moving up. So how do you move a graph upward? Yeah, you add a number. So I'm going to start off by just making some notes over here. So if I have f of x equals x squared, and I could go ahead and say if I add a number to it, so plus a number, that's going to move the graph up. Right? Now I'm just using the pound sign. You could say anything. And I'm going to go into, I suppose what they did is they wrote k, didn't they? Can we all agree that we're going to use the number k to represent any number you wish? Okay, so if I add a number, it moves the graph up. Now likewise, what if I take my function x squared and I subtract a number? Then what happens to my parabola? Whoa. Yeah, you start moving down, 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 down. So, wait a minute, class ends at 10:20? Mm-hmm. Yeah. Oh, so I was completely wrong when I said that we had 40 minutes left. Did you all think I was just messing with you? Mm-hmm. Oh boy, I wasn't. I thought we went until 40. Well, that's okay. We're going to finish introducing this idea. Okay, so if you subtract a number, that means you're going down. So now we have, oh boy, x squared minus k. That means you just move the whole function down. Now, what I'd like you to notice is that I added k and subtracted k to the function itself. And I would say outside the function. Because the function is x squared. I didn't change x squared inherently. I added something to the outside of x squared. Whereas now, what if, instead of adding a number or subtracting a number to x squared itself, what if I went inside the squaring function to x? And I started manipulating x itself. What if now I take my x and I start adding a number to x? What happens to my function? Yeah, kind of counterintuitively, it moves to the left. So now if I jot down x, now I'm doing it inside. If I add a number to x, that actually moves it to the left. And so you can probably all guess what happens if I start subtracting a number in there. If I subtract a number, what happens to the function? Yeah, it starts moving to the right. By that amount, right? We haven't said that yet, but by that amount. Okay, so now if I go ahead and say x minus k, then that actually moves it to the right. So let's just talk and notice what just happened here. If you add or subtract a number outside the function, it matches your expectations. So the positive means up, negative means down. Whereas if you add or subtract a number inside the function to x itself, and keep in mind, x-axis, x moves left and right. If you add or subtract a number to x itself, which represents the left and right direction, then it moves left to right, but opposite of what you'd expect. So in this case, it's the opposite of what you'd expect. But in the case of adding it outside the function, it's the same as what you'd expect. So that's pretty important in terms of just being able to look at a function and knowing what's happening. So for instance, what if right now I said, hey, here's a function, and it's x minus 3 squared plus 2. How would you interpret this? This is a parabola because it's x being squared, but first of all, did I move it right or left? Right 3, and then did I move it up or down? Up 2. Right, so what we're talking about right now is training your brain to be able to look at this information and carefully extract the meaning. That if you're adding it or subtracting it to x, it's the opposite of what you think, left or right. So negative really means to the right. And if you add it outside the function, then positive and negative mean what you think they mean, so plus means up. Okay, so that's the first couple. The next one, which is pretty straightforward, is what if I put a negative sign in front of the function? I think you all know what that does. It flips it upside down. So if you put a negative outside the function, it'll flip it upside down. So now we have x squared with a negative outside. That just flips upside down. So again, when you do something outside the function, it's a vertical motion. Up, down, flips it upside down. What if you put the negative sign inside on the x? Well, how would that flip it? Instead of flipping something upside down, it would flip it right side left. Nobody really says that. You flip it upside down, you flip it right side left. Yeah, flip it side to side. So that flips left to right. Okay. Well, that covers the first few graph transformations that we'll be talking about. And I'm just about out of time. There's just a few more problems left on that, and then we'll start chapter 2. And that's where we start on Wednesday. So today's Monday. We will wrap this up on Wednesday. I don't think I have anything else to say right now. I would go home tonight and immediately wrap up whatever old homework you have, sections 1.1, 1.2, 1.3, 1.4, and go ahead and try all of section 1.5 and 1.6. And then hold off on 1.7 until Wednesday. Thank you, folks.